This is the second and last lecture on proving that the modulus of all path connecting the two boundary components of an annulus in the plane is specifically the number shown here, which depends on the log of the ratio of the inner and outer radius. We've talked about this and why it has the right asymptotic behavior as R1 goes to 0. In previous lecture, we showed that this specific function rho star is indeed admissible by proving that when you integrate it along any curve in the family, the line integral adds up to at least 1. And we saw that this is not actually trivial. Indeed, that lecture is the most difficult part of this proof. As you will see, the reverse direction that I'm about to show is a rather straightforward application of the integration in polar coordinates. The previous lecture required some topological argument as well, so please do check that out. Once you know that a particular function is admissible, of course its L2 norm, and here we're talking about mod 2 in fact, which is the L2 integral, then whatever that number is, it's an upper bound for the modulus. So at least you have one function with L2 energy equal to alpha, so modulus by definition is infimum of all such L2 integrals, has to be less than alpha. So to complete our proof, we have to go in the opposite direction and show that if now you start with any random admissible function, then its L2 integral can never be less than alpha. You cannot do better than this rho star in terms of L2 energy. So how does one prove this? The fact that makes this so easier is that instead of now working with random curves connecting the two circles, which can in general look very, very wild, you can only look at the radial segments. So segments like the ones that I have tried to draw in blue that are along the radial directions from the center of the annulus, and simply connect the two circles. So in particular for such gamma, we see that rho, by just being admissible, is bigger than or equal to 1. So on each of these radial segments, the integral is bigger than 1. That we know. Then, so let's say integral rho over d gamma s is at least 1 for every radial segment gamma, which I don't want to write down. I just specified verbally what I mean by this. We want to estimate from below the L2 integral. So I want to integrate rho dx dy, and I want to estimate it from below, so I can actually say I even don't need, because these gammas are contained in the annulus, I only need to integrate over the annulus this rho dx dy. And then from integration in polar coordinates, because the annulus is rotationally symmetric, it's easier just to switch to polar coordinate, which will be from 0 to 2 pi, integral over gamma, say gamma theta, which is the 1. So gamma theta is the radial segment in direction of theta, making the theta angle with the x-axis. So gamma theta rho, which will be described in now polar coordinates, and then there is r dr d theta. So this inner integral, you parameterize this gamma theta in terms of r, and then you do this one. Now, here is where we want to put the lower bound on this thing and then continue. So let me call this quantity this heart, and we will continue estimating heart from below down here. So I want to find an estimate of this quantity, this integral. However, I know that integration without this r factor is bigger than 1. The clever way to get usually a connection between such objects is the use of Hölder's inequality. So I know that this is bigger than 1, rho ds gamma, which after these transformations, this will be rho dr gamma direction theta. And I want to end up with ultimately in estimating rho r dr. So there is this r appearing here, and that doesn't exist here. So what I do is I bring in this r, and I also take that away. By the way, I have made this tiny blunder. I want to estimate rho squared, of course. So I want to get rho squared. So I can bring this in. I can bring any power of r here, and it's negative without altering that. So this is just an equality. And now I will apply Hölder's inequality, or you can call it Schwarz inequality. And I want to raise this to power 2. And after I raise it to power 2, I want to end up with this. So therefore, I will put 1/2 and negative 1/2. So Hölder's inequality will give me gamma theta, this thing, to power 1/2. And then it will give me integral of r to negative 1 dr over gamma theta. Integral of r to negative 1 over, so we are close to estimating this thing because here we have 1, but now we have to get rid of this and find some estimate for that. So let's see. I want to integrate, so without loss of generality by symmetry, I can imagine that I'm going in the horizontal direction. So I'm integrating over this, the function, so it will be from r1 up to r2, 1 over r dr. And that will be log of r2 over r1. Let's call this beta, as we've done before. And this will be the same if I integrate over any other gamma theta. It's exact same picture in all directions, and an exact same quantity being integrated. So therefore, putting these last two things together, we see that beta inverse is less than or equal to integral rho squared r dr gamma theta. I want to also get rid of 1/2 power, so this will be negative 2. So I raised both sides to power 2. Now I have this for every theta direction. Therefore, I go to this heart, and now I replace this with the lower bound. So heart, which is, let's see why this is even important, because this is integral rho squared over r2 of dx dy. This will be bigger than or equal to integral from 0 to pi of this quantity, which we have estimated from below by beta to power -2, and the theta. Okay. Great, except that I have this discrepancy with, oh, okay, now I see. So let me make my correction in red. So I rushed too much here. So this is also to the power 1/2. So this will be just, this would have been beta to 1/2 on this side. So this is still just -1. So this is -1, sorry about that. It's the nice thing about knowing where you want to get, knowing the final answer is you immediately know you have messed up. So this will be equal to, because, well, it's independent of theta in fact, so this would be 2 pi beta to -1, which is just alpha. So we have proven that if you start with any admissible function rho, its L2 integral is bigger than or equal to alpha. And thus mod gamma mod 2 gamma is at least alpha. And we've seen that it's less than alpha. We're done. Okay, so this is one of the most important facts about modulus in the complex plane. Let me show you an immediate consequence. Modulo, you have to, for now, believe this fact that if f is from omega to omega prime is conformal map, where these omega and omega prime are, say, connected open sets, and gamma is a path family in omega. If I have previously used also curve family, they are to me interchangeable terminologies. Then modulus 2 of gamma is the same as modulus 2 of f gamma, where by f gamma we mean the collection of f composed with gamma, where gamma belongs to the family gamma. So if you have a path, then composition with f is still a path because f is continuous. Well, it's much more than just continuous. And if gamma is rectifiable, then so is f o gamma. So this is a very deep fact, but very easy to prove. I will prove it in some lecture from complex analysis, that the modulus 2 is invariant under conformal maps. So if we now believe this one, plus the modulus calculation, we have the following consequence, the corollary of the theorem. Two annuli in C are conformally equivalent, which means simply that there is a conformal map between them. Conformal maps have a conformal inverse, so it only suffices to say that there is one conformal map from first annulus to the second, then automatically you have its inverse giving a conformal map in the opposite direction. So if two open sets, there is a conformal map from one of them to the other, we call them conformally equivalent. So two annuli in the plane are conformally equivalent if and only if this ratio in the first one is exactly equal to the ratio of them in the second annulus. So the notation should be here self-explanatory. So here I have R1 over R2. And then here I have another annulus, hopefully I can draw this, of different size. And these will be conformally equivalent. There will be a conformal map from this to that, if and only if these are equivalent. So proof, well, if there exists some conformal map from annulus A to A prime, and then for gamma equal to, again, the same collection of gamma joins boundary to boundary, okay, joins the two circles of A, of the family above, where we calculated the theorem for. Then for this, we have that f of gamma is exactly the family of curves in A prime, in the target domain, where gamma joins circle to circle. Here we have to be careful a bit, but it's very easy. The proof that we have given will work just equally as well if we, in our path, we only restrict it to paths that remain within the boundary. Because if a path is outside, goes outside, then f gamma wouldn't make sense. So we have to redo the proofs above, and it's easy to check that we never used any fact about path also being able to leave the annuli. So if we restrict only paths that remain within the annulus, it will be true that their images will also remain here. And what I'm trying to show here is that if you have a curve here, it does equal. So if you have something here, then there does exist some gamma such that gamma tilde is f of gamma. Simply take gamma to be f inverse, which is another homeomorphism of this gamma tilde. So there is this one-to-one correspondence between the path family here and there. And again, the theorem we've done equally as well, the proof works to show that modulus of gamma is, well, 2 pi log of r2 over r1 to negative 1. And now from the invariance of modulus, this will be modulus of f gamma, which we said is the family of path in the target annulus, and it covers all of them. So again, apply the theorem to see that this is log of r2 prime, r1 prime to negative 1. And these two quantities can be equal because log is 1 to 1 if and only if r2 over r1 is r2 prime over r1 prime. So this proves that to have any chance for finding conformal map, you first need to have this. So this is a necessary condition, but is it sufficient though? So for sufficiency of these conditions, if r2 over r1 is equal to r2 prime over r1 prime, then a simple scaling and translation in C takes A to A prime. So you start with this smaller A annulus, then you can dilate it to so that the inner circle becomes exactly the outer circle. So you do this translation, so you multiply by r1 prime over r1 times z, We don't even need to assume this R1 is the smaller of them. So this is just the scalar multiplication. This is conformal. And the inner circle maps to inner circle. But because the ratios are the same, it happens that the outer circle also overlaps now with the circle of radius r prime, r2 prime, so that this becomes a copy of a prime. And if we exactly want to have the same center, then just translate this, shift it very rigidly so that center is center. And again, this is just conformal. So composition of conformal is conformal. So very interesting things come out of modulus. This is super easy proof once you know modulus is invariant. But think about a direct way of showing that if the ratios are not the same, there is no conformal map between them. So let me know if you like this subject of conformal modulus. It has a lot of applications to complex analysis, and later the theory of quasi-conformal maps, which is a very deep theory in geometric mapping theory. It generalizes the notion of conformal maps so that we can talk about them in higher dimensions and also even in metric measure spaces. And this quasi-conformal map theory makes a lot of use of modulus. Actually, one definition of quasi-conformal maps is exactly by appealing to the notion of modulus. Until next lecture, have a great time and thanks for watching.